Hello, I'm Cheng-Wei Lai. Today, I'd like to share my background and my interest in research. I come from Hsinchu, Taiwan, a city famous for its semiconductor industry, where TSMC was founded. I majored in chemistry at National Tsinghua University, and now I'd like to introduce my undergraduate research. During my university years, my research focused on water bridge. Since I was conducting experiments in a soft matter physics lab, this research primarily involved condensed matter physics within fluid dynamics. The water bridge phenomenon refers to the phenomenon where, when a high voltage current is applied to two beakers filled with deionized water, the water spontaneously forms a bridge connecting the two beakers. This phenomenon has been observed for 130 years, but due to the nature of high voltage electricity, the underlying physical mechanism is difficult to elucidate. My contribution to this research was designing a dye experiment adding electrically neutral polyvinyl chloride (PVC) particles unaffected by the electric field to the water flow, and using particle image ferrosymmetry to analyze the flow field, discovering the bilateral ionic flow phenomenon. In other words, the water bridge has a dynamic structure. The outer layer of the water bridge is negatively charged, flowing from the negative pole to the positive pole, while the inner layer is positively charged, flowing from the positive pole to the negative pole. This discovery became my first research project. Next, I'd like to introduce my second research project during my master's studies, which focused on glycerol bridges, specifically replacing the water in a water bridge with glycerol. Glycerol bridges are prone to breakage and are difficult to maintain for extended periods. However, I unexpectedly discovered in my experiments that glycerol drops can be suspended in the air under the influence of an electric field. This phenomenon was observed for the first time. Therefore, I decided to capitalize on this unexpected discovery, reproducing the experiment and standardizing the experimental technique. I also completed qualitative testing of the experiment before submitting it to my colleague in the physics lab for the thesis. The key characteristic of this glycerol drop experiment is that it utilizes plasma to neutralize the charge on the glycerol drop. After the charge is neutralized, the charge on the glycerol drop changes. Under the influence of a strong electric field, it moves in the opposite direction, creating a back and forth oscillation. This is the highlight of this research. After graduation, I chose to work in industry to hone my experience. When I started working in 2021, the AI wave was just beginning. My first company, DuPont, started using AI to optimize its production processes. Inspired by this, I decided to teach myself deep learning and obtained my NVIDIA certification. AI technology is a double-edged sword. On one hand, it's incredibly convenient, but on the other hand, it decreases 30% of job openings. I believe that in the future, the ability to write AI code will be an essential skill. That's why I do the self-learning on AI project and got the AI certificate. In addition, at DuPont, I learned how to assist in the development of Cooper piping solutions, which marked the beginning of my work in the electrochemical industry. At DuPont, the solution formulas were essentially fixed. Employees tested different plating conditions. This made me realize that different plating conditions could significantly affect the plating results. Furthermore, to protect patents, everyone's role was highly specialized, ensuring that no one could replicate the company's entire technology. This is a key consideration in product development within a commercial company. My second job was at Phoenix Pioneer Technology, a small IC substrate company. Simply put, the IC substrate is the wiring for the chip. The chip connects to the circuitry through the IC substrate to perform its computational functions. My position was a process engineer responsible for the production of the pre-plating frame. The PPF facilitates IC substrate processing, such as connecting gold wires to the chip or soldering to the motherboard. The PPF enhances the IC substrate's ability to connect to other components. However, during the process, in addition to the thickness of the nickel, palladium, and gold plating, the appearance of the finished product also needs to be considered. Because the PPF is the product's appearance, it must be very beautiful and intact without any damage or discoloration. Generally, in academic research, the focus is on the reproducibility of experiments, neglecting exceptional cases. However, when managing a manufacturing process in an industry, I need to pay attention to anomalies or exceptions. This was a very unique experience. In the final section, I'd like to discuss a research project that interests me. I'm very interested in electrochemistry. Both my research in school and my work projects have been related to electricity. I find electricity to be a truly fascinating phenomenon. Among my most interesting areas are electrolytes in applied solutions. Electrolytes play a role of salt bridge in electrochemistry, and their composition is crucial in electrochemical batteries, such as lithium-ion batteries. Now, substances can become electrolytes. Table salt can be an electrolyte, but sucrose cannot. I was inspired by band theory. Band theory explains that substances can be classified as insulators, semiconductors, and conductors based on the size of the band gap. I'm considering whether this can be applied to electrolytes, classifying them to non-dissociated electrolytes, semi-dissociated electrolytes, and dissociated electrolytes. Band theory has significantly spurred the rapid development of the semiconductor industry because the properties of semiconductors can be used to generate circuit signals. Similarly, If we developed semi-dissociated electrolytes, could we develop liquid semiconductors? The biggest drawback of the current solid-state semiconductors is their vulnerability to water. If we developed liquid semiconductors, could we solve the problem of water resistance in electronic devices? Water-resistant electronic devices could be used in marine engineering, such as offshore wind power and tidal power generation. Furthermore, semi-dissociated electrolytes with different conductivity properties could also be used in the development of electrochemical batteries, such as lithium-ion and sodium-ion batteries. Therefore, systematic research on electrolytes has a wide range of potential applications. That is why I'm very interested in this topic. That concludes my video. Thanks for watching.